Hello and welcome to section 3.5 limits at infinity, and so we're going to go through today and find limits at infinity. And so this should be a little bit of a review of limits for you, so hopefully it's not a terrible situation for you, but we're going to go through and ask you to find the limit as x goes to infinity for each one of these. So I'm going to break this up into two different things and say as x goes to infinity for 5 minus the limit as x goes to infinity for 2 over x squared. Well, the limit of anything going anywhere of a constant is just that constant, so we get 5 minus, now if I put in infinity in for x using kind of direct substitution the way we used to, we would get 2 over infinity squared. And if you think about infinity being a really, really large number, 2 divided by a super large number is going to be so small that we're not going to be able to tell the difference between the number and 0. So we're going to call that 0. So our answer for this problem is a limit of 5. And it's because of the constant. So then in the second example, we're asking you to find the limit of something like this. And if I was to break it into division property that said, oh, I could do the limit of the top divided by the limit of the bottom. Well, if I do the limit and I put in infinity in here, the top would give me 2x minus 1. The limit of it as x goes to infinity would be infinity. And likewise for the bottom, the limit as x goes to infinity of x plus 1 would also be infinity. So this is kind of our indeterminate form, just like we had before where we had 0 over 0. So this means I got to do a little bit more work in order to make this work. So what I do mathematically is say, okay, well, what is the largest power on the bottom? The largest power on the bottom is x. So I take everything and divide it by that largest power. X, and we do 1 over x, and go through and do some simplification. And when I do this, my limit as x goes to infinity, well, I end up with 2 on top minus 1 over x, and we have 1 plus 1 over x. And so if that's the case, when I do limit goes to infinity, since this number is a small number over a very, very large number, this guy is basically 0. Likewise, this guy is basically 0. And so you can see that I'm going to end up with 2 over 1, which is really just a limit of 2. Now, this actually fits one of our properties when we talk about the what's the horizontal asymptote. This has been one of our things we've been teaching you guys for years. What's the horizontal asymptote without actually giving you a reason why it works. And the horizontal asymptote, remember, is a limit at infinity. So this is since the degrees are the same. Since the degrees are the same for both of these guys, they're both 1. Our leading coefficient is 2 over 1, which gives us horizontal asymptote, or a limit at infinity of 2. And that's really what we're dealing with, is that you got to understand that limits at infinity and horizontal asymptotes kind of coincide. And so knowing that, you might be able to figure out these guys just from our rules for horizontal asymptotes that you've learned in the past, but we'll do it and explain it calculus-wise, limits to infinity. And so basically what I'm going to do is I take, since this top part would be infinity and the bottom part would be infinity if I did direct substitution, that's what we always start with, well then I have to do some more work, so that means I'm going to divide everything by x squared, because that's the highest power on the bottom. So my limit as x goes to infinity of this is going to be 2x over x squared plus 5 over x squared. And on the bottom I have 3x squared over x squared plus 1 over x squared. So we're going to simplify as much as we can, and so my limit will change to 2 over x plus 5 over x squared all over 3 plus 1 over x squared. Well, remember that if you have a small number over a really large number, that's 0. So when I take my limits now, I get 0 for that term and 0 for that term. This guy also becomes a 0. So I'm really left with 0 over 3, which means my limit is 0. So my horizontal asymptote when the top power is smaller than the bottom is 0. Well, now if I was to do the next one, same thing will happen. I'll get infinity over infinity. So I got to break this up and say, okay, my limit as x goes to infinity for this, I'm going to divide everything by the highest power on the bottom, which happens to be x squared. And so I get this. This is like the previous example that we just did. And so by doing all of this, if I rewrite my limit, I end up with, and this will also work for negative infinity, just so you know. This one becomes 2 plus 5 over x squared, and then this is 3 plus 1 over x squared. So if this is the case, then you'll notice that when I take my limit to infinity, these guys become zeros, and I'm left with 2/3 as my limit. And that's really what we're doing. So now, looking back at what we learned about horizontal asymptotes, when we had the same power, we just took the leading coefficients, and that gave us our limit. That gave us our horizontal asymptote, which is 2/3, and that's the same thing that happened here. So now we have the power higher than the top is higher than the bottom, and so when I do my limit to infinity in this example, in this one, I'm going to do the same thing. I'm going to divide everything. Since I get infinity over infinity again, I am going to divide everything by x squared, so I get 2x cubed over x squared plus 5 over x squared divided by 3x squared over x squared plus. And so I get something that looks like this, and if I simplify this, my limit changes to 2 over, or sorry, let me write that again. I was going to say 2 over x, but it's actually 2x plus 5 over x squared. And on the bottom down here, I get 3 plus 1 over x squared. And so when I take my limits to infinity, these guys become 0, like they always have. But now I have infinity times 2, which gives me infinity on top all over 3. And taking a really large number and dividing it by 3, infinity dividing by 3, doesn't change it any, so it's still infinity. And so that's the limit that I get for this guy. Is that it's infinity, and so this is an infinite limit, so the limit basically will keep increasing without bound, meaning we don't have a horizontal asymptote, and we'll talk about what happens with those asymptotes in a little bit in the future. If you don't remember, it becomes an oblique or a slant asymptote. So then the next one, if we're dealing with square roots, so we have, it's still the same idea whether we're going to positive infinity or negative infinity, and the same thing with the previous one. So what we're going to do is we're going to go through and divide by the highest power on the bottom. Just like before, because I still get infinity over infinity when I plug in my infinity. So what I'm going to end up doing is when I rewrite my limit, I'm going to divide everything by the highest power, which happens to be the square root of x squared down here, because this whole thing is under the square root. And so if I write my limit as x goes to infinity, now I could write it as 3 over the square root of x squared, which is also x, minus 2 over x. And if you don't like that, I'll do this. That's fine. I'm okay with this. But just remember that that's just an x. And then on the bottom, I do the same thing, and I say 2x squared over x squared plus 1 over x squared. And because I left them underneath the square root, I don't have to put another square root symbol there. And so now on top, I'm left with 3 minus 2 over x. And on the bottom, when I divide this, I'm left with the square root of 2 plus 1 over x squared. And so now when I take my limit, as this limit goes to infinity, and I should have written limit there instead of an equal sign, as x goes to infinity, then I end up with 3 on top over the square root of 2. And so that's my limit as my x goes to infinity. Well, does it change much when we deal with a negative? Well, not really. The only difference is when I divide, I have to have a negative sign somewhere in here to take into account what's happening, and it really doesn't matter which way you like, where you like to put it, but I'm still going to divide by the square root of x squared, top and bottom, which will change my limit to x going to negative infinity. And this is the one trick with negative infinity for square roots. You don't have to do it so much with the other ones. You can just make them negative. But I'm going to say, okay, I'm going to divide this one by my square root of x squared. minus 2 over the square root of x squared. And then on the bottom, I'm going to do the same thing, but I'm going to take this guy, I'm going to break this apart. I'm going to break it into two different things and say, it's going to be 2x squared plus 1, all divided by the square root of x squared negative. Now it's the same type of thing as what I was doing up above. It's just I'm just taking track that I got to have a negative because I'm going to negative infinity. Now I could have put that negative up top. It would have done the same thing. It wouldn't matter. You just have to somewhere take into account that you're going to get one negative sign popping up. And so with that happening, then on top I'm still left with 3 minus 2 over x, and on the bottom it changes signs and I get negative, and now I could write it the way I did before as 2x squared over x squared plus 1 over x squared. And so now there's my negative sign that I picked up when I just pulled it out and then put it back underneath like I did before. Now I'm left with, when I take my limit again, this guy is 0, this guy is 0, and now I'm left with a 3 on top over a negative square root of 2, or I can just put the negative there. And so the only thing that happened is I changed directions. So then we got to talk about trig functions. What happens when we go to infinity for trig functions? Well, this top one, if you remember, sine is just like this. It's just a function that goes up and down, and it goes from positive 1 to negative 1, and this is an oscillating function. So since it's an oscillating function, the limit does not exist. So this one is still, the limit does not exist because we have our oscillating function. But then how does it affect this guy when we divide sine of x by x? Well, that would be the same as saying, well, we were going between negative 1 for sine of x, sorry, got ahead of myself there, for sine of x, and between positive 1, and so that's what we're dealing with. But since we were doing sine of x over x, we're dividing these guys, everybody by x. And so then if I'm doing my limit for each one of these guys, I'm going to say, oh, well, my limit as x goes to infinity for negative 1 over x, and my limit as x goes to infinity for 1 over x, well, that should be the notice that you're going to get 0 for these guys, because that's what we've been doing in the previous ones. And so by the squeeze theorem, we can say that the limit as x goes to infinity, the limit as x goes to infinity, since sine is between negative 1 and 1, and sine over x is between these guys, we can use the squeeze theorem that says as x goes to infinity of sine of x over x is that we're going to get 0 because we have one function that's going to 0, the other function that's going to 0. So therefore, as they squeeze together, the function that's in the middle is going to have to go to the same spot. And that's what the squeeze theorem is all about. So then in our next example, we're talking about oxygen levels in a pond, and basically we're talking about it's non-polluted. We're going to have this waste dumped in there, and it's going to oxidize, and we want to find the percent of the normal level of oxygen that exists after 1 week, 2 weeks, and if it approaches infinity. So if I want to find out what's happening after 1 week, that's just as much as saying f of 1, and so plugging 1 in, I get 1 squared minus 1 plus 1 all over 1 squared plus 1, and I end up with getting about a half, I believe, which is about 50%, is what exists left in the pond. After 2 weeks, then we are going to plug in 2, and we'll say, well, it's 2 squared minus 2 plus 1 all over 2 squared plus 1. And when I simplify that, I get 3 over 5, which means it's about 60%. And so then as the weeks go on, after we pollute it, where the weeks go on, it's getting better and better. So then if we take this thing out to infinity, what's going to happen? So I'm going to do my limit as x goes to infinity of this function, and we have t squared minus t plus 1 all over t squared plus 1. You'll notice that as I do this, highest power is t squared, so if I divide everybody by t squared, and I just just like we have before, because the way it was, the two polynomials would be infinite, and so we'd end up with infinity over infinity. But on top, if I do some simplification, my limit as t goes to infinity is going to be 1 minus 1 over t plus 1 over t squared. And on the bottom, I'd get 1 plus 1 over t squared. Now, if I actually take my limit, remember this guy is 0, this guy is 0, this guy is 0. So as this thing goes on forever, we're going to end up with 1, which means we're at 100%. So the pollution would go away. The pollution would go away. The oxygen level would be back if we had a long enough time. So then, in the next one, if we want to find the limits to infinity of something like this, where it's just x cubed, if we did direct substitution, we're talking about infinity cubed, which is just infinity. And if it's negative infinity cubed, well, because it's negative and we're cubing it, there's 3 negatives being multiplied together, so this would be negative infinity also. And then my final example, we want to find the limit of this guy, and you'll notice that in this case we end up with well, if I plug in, hopefully you can see, remember our horizontal asymptotes, that we have the higher power on the top than on the bottom. We're going to end up with a situation where this thing is not going to be super nice to us, but we're going to end up with some kind of slant asymptote or something like that. So what we have to do is, on top I get infinity. So if I go ahead and do what I've done, let's just go through and do what we've done in the past. As x goes to infinity, if I divide the top by, I get 2x squared over x minus 4x over x, all divided by x plus 1 divided by x divided by x. I end up with infinity over 1, which is not a very good number for us, but we know that we now have a slant asymptote. The other option is that we could go through and actually find out what the slant asymptote is by doing long division, and I would highly recommend that you do this. Go ahead and divide in x plus 1 into this and see what you get, and then use that as your guide. But in either case, you're still going to end up with infinity for this. So if I divide, I'm going to get 2x into this, so we get 2x squared minus plus 2x. When I change the signs on the bottom row, I end up with negative 6x, and then it would be plus 0. And so then to make my first term, I'd subtract 6, and so I'd get minus 6x minus 6, and changing the signs on the bottom row, that's a 0 there. Changing the signs on the bottom row, I end up having a positive 6, so I get 6 over x plus 1. And so now you can see that this guy is going to go to infinity. We're going to subtract 6, and then this guy will go to 0 when it's all said and done. And so since that's going to go to 0, then I still have infinity as my solution. Same thing will happen with the next one. I'll end up with negative infinity, and if I did long division, I would find that 2x minus 6 is my slant or oblique asymptote, and hopefully you remember that from Algebra 2 and pre-calculus. But this guy will also go to negative infinity, and so remember, if you have any questions on any of this stuff, please come to class prepared to ask them.